Good evening. Welcome to part 2, the real part that you came for. It's a pleasure to welcome you to the third Carnegie Astronomy lecture in the 2018 series here at the beautiful Huntington Library. For those of you who haven't met me, my name's Erica Clark, and for the last 5 years I've been working closely with Dr. John Mulcahy, the director of the Carnegie Observatories, and other scientists and staff in helping to organize these lectures and many other events. It's also because I'm working with Dr. Mulcahy that I'm standing here this evening because, as many of you know, he's serving as interim co-president of the Carnegie Institution for Science in Washington, D.C., which is our parent institution. And he's extremely sorry that he can't be here, but he'll be back for the next lecture, and I hope he's watching on the live stream right now. Hi, John. Before I introduce tonight's speaker, let me congratulate all of you who scored a seat for tonight's lecture, because the tickets were fully booked within 28 minutes of going online. So we're delighted that our astronomy series attracts such an enthusiastic audience from throughout the community and beyond, and that the Carnegie Observatories is part of a community that values scientific research and astronomy so highly. It really means a lot these days. So with your enthusiasm also in mind, a few related announcements before I introduce Dr. Eisenstein. First, a reminder to set your alarms for 10 a.m. tomorrow morning, when tickets will be released for our final lecture of the season. We expect they'll be gone in, 3 minutes? Someone said, "What are you, U2?" On Monday, May 21st, Dr. Maria Drought, who is a Hubble Fellow and one of our great young postdoctoral fellows at the Carnegie, will tell us about the origins of the elements in her talk entitled Astronomical Alchemy. We're also very pleased to tell you about 2 series underway, about to be underway, with our friends at the Mount Wilson Observatory, a new astronomy lecture series and a continuing concert series, both in the dome of the historic 100-inch telescope. To find out more, visit mtwilson.edu. And I also encourage you to visit the current exhibition here at the Huntington. It's a series of exquisite large lithographs by the French astronomer and artist E.L. Trouvelot. They date from the late 1800s, and they're of comets and planets, the aurora borealis, and other celestial objects. And if you haven't already, I encourage you to sign up for the Carnegie Observatory's newsletter to stay up to date on our latest scientific discoveries and events. You can do that online or in the lobby tonight after the lecture. I also want to take this opportunity to say a few thank yous, which are extremely due. We're especially grateful to the Huntington staff. Their unflappable expertise has been a great support throughout our lecture series. This is the 16th season, and they've been with us for those seasons. A special shout out to Ben Tubble, our great audiovisual engineer, who's up there in the booth. And profound thanks as well to the great Carnegie staff and scientists and others who make these events happen. It's a great, great team. And last and not least, a special thank you to the Norris Foundation, whose generous support makes this lecture series possible. And now I'm really delighted to introduce tonight's speaker, Dr. Daniel Eisenstein. It's a special privilege for me to do this for many reasons, because one of the reasons being I've known Daniel since childhood. And suffice to say that even then, his teachers and his mentors recognized his prodigious scientific gifts, which will be evident tonight. Dr. Eisenstein also has a special connection to the Carnegie Observatories because from 2007 to 2015, he directed the 3rd phase of the Sloan Digital Sky Survey, which are the most detailed maps of the universe ever made. And it's also an international collaboration that has been one of the most influential projects in the history of astronomy. Carnegie is proud to be a partner in the Sloan Digital Sky Survey, and now Dr. Juna Kohlmeyer, whom many of you know and who's one of our great scientists as well, is director of Sloan Digital Sky Survey 5, And the DuPont telescope at our Las Campanas Observatory in Chile will again map the southern hemisphere. So, finally, to Dr. Eisenstein. Dr. Eisenstein received his PhD from Harvard in 1996, and then held postdoctoral positions at the Institute for Advanced Study, the University of Chicago. In 2001, he joined the faculty at the University of Arizona, and 9 years later, he moved to his current position as professor of astronomy at Harvard University. In 2014, Dr. Eisenstein was the joint winner of the 2014 Shaw Prize in Astronomy, which is often called the Nobel Prize of the East. And in the same year, he was elected to the National Academy of Sciences. His talk tonight is related to his groundbreaking work in cosmology. Please give Dr. Eisenstein a warm welcome.
Well, it's a great pleasure to be here tonight. When I picked this title, I assure you I did not know there would be a musical prelude, but it, it really does fit. So I'll be telling you about our studies of cosmology and this phenomena called dark energy, and how we're trying to study it using sound waves that propagate in the very early universe. One of the things that's really nice about giving this talk here is that so many of the threads of modern cosmology actually were really pursued by astronomers in the Pasadena area. So it's, there's a lot of historical aspects of this as well. Okay, so I will be starting by giving you an introduction to cosmology and dark energy, quickly, and then telling you about these sound waves, which go by the fancy name of the baryon acoustic oscillations, and how we use those to map the universe. And then I'll tell you about the Sloan Digital Sky Survey, and then I'll be describing some of the cosmology that we've learned from the acoustic oscillations in the SDSS. So I want to start with a big picture question. So what is the universe made of? Of course, that's a very important question. And it turns out to have a very surprising answer. So, of course, one aspect of this surprise is this idea called dark matter. So this was really first seen in the clusters of galaxies by Fritz Zwicky about 80 years ago, and then really pursued vigorously by Vera Rubin and collaborators studying the scale of galaxies. And the basic idea here is that as galaxies rotate inside clusters or stars rotate inside galaxies, they are moving too quickly. And so if we really had only the matter that we see, only the gravitational forces that we see, those stars would fling outside of their galaxies and the galaxies would fling outside their clusters. So we infer from these motions that there must be additional mass inside of the clusters in the galaxies. And moreover, we have since learned that this material really is not the familiar stuff of protons and electrons and neutrons, or even neutrinos, but is actually some new exotic form of matter. Well, of course, this is a very provocative thing, and astronomers set out to try to make a more complete census. And as we looked from galaxy scales up to cluster scales, we found there was more and more dark matter. And so as we go out to larger and larger scales, we're trying to use the motions of things to infer the amount of dark matter. And the biggest thing you can measure is the overall expansion of the universe itself. So people set out to do this with the idea that if you have more material in the universe, the expansion should slow down over time. It should decelerate because of this additional material. Well, I've just mentioned the expanding universe, so I should pause to explain that. Of course, that was very famously demonstrated by Edwin Hubble here. So the idea here is that when you look at distant galaxies, you see that and you separate their light out into a rainbow. You see characteristic transitions or dark spots in the spectra, and these correspond to particular transitions of atoms in the atmospheres of stars in those galaxies. And when we measure them, we find that they are actually shifted to the red. Their wavelengths are shifted to the red relative to what we measure in the laboratory. And we interpret this as saying that the galaxies are moving away from us, and we're seeing the Doppler shift of their light, just like an ambulance streaking away from us would have its sound shifted down. And of course, the wonderful thing is that if you have a uniformly expanding universe, then you find that the more distant objects are moving away from you more quickly. So this is just like if you and your row of seats all took one step, all had to move one to leave one blank seat between each of you. Your neighbor would move one seat further, but the person 3 down would have to move 3 seats further, and the person 10 seats down would have to move 10 seats further, and so they would actually be moving faster away from you than the person immediately on your left. So this is called the Hubble relation, and the idea is that the velocity should be proportional to distances for small distances. And we will get back later to the questions of what happens when distances get to be cosmologically large. So this idea of measuring distance or redshift really shows that the universe is expanding. And in fact, it's such a ubiquitous measurement for us that astronomers very often measure past epochs and past distances by the redshift, because it's the thing that is most easy to measure. So I will very often in this talk say things like at redshift 0.5 or at redshift of 1. This corresponds, in my mind, to a past time, not so much to the actual spectral measurement. So let's see what this stuff infers. We want to, again, try to weigh the universe. So if we have a schematic plot here of time versus the size of the universe, if the universe had no forces on it, if it was just expanding ballistically, then you would get some straight line, and the slope of this line today would correspond to the so-called Hubble constant, the relationship between velocity and distance. And we would be sitting here, but if we looked back to some previous time, like redshift of 1, we would have some look-back time. And if the universe were decelerating, then it should be expanding more quickly at early times and slowing down more recently. And so that would actually correspond to having less time to a given redshift, a given size of the universe. So when the universe was half as big, it would not be quite as old as in the universe that had no material. So the idea is that by measuring this time, you can start to infer how much material there is in the universe, because the more matter there is, the more this blue curve will deviate from the black. So people went out to do this, and they found a very surprising answer, which is that in fact the high redshift objects were actually too faint. They appeared to be too far away, or the look-back time was too large. That corresponds to a plot like this, that actually we seem to live in a curve more like this red line, where the universe is older at a given age. There's more time, more distance than we expected. So this implies that the universe, that the expansion rate is actually accelerating today. Now, it was decelerating in early times, we think, but more recently it's been accelerating. This is an extremely bizarre thing. It's like you throw up an apple up in the air, and it comes down and hits you on the head instead of coming down and hit you on the head, it actually accelerates out into outer space. It's very strange. So we label this cause as dark energy, which I think actually overstates our knowledge by a factor of 2. All we really know is that it's dark. We don't really know that it's energy, but nevertheless, that's the name that's given to it. And it's a very important effect, because actually the dark energy outweighs all the rest of the stuff by a factor of something like 2.5 to 1. So it's a very, very important part of today's universe. So what's the cause? Well, the short answer is we don't know. There have been many possible explanations advanced, the most famous of which is the idea from Einstein called the cosmological constant. But there's many other ideas. It might be some new force of nature. It might be some modification to a known force, i.e. gravity. It might be some artifact of extra dimensions from a string theory. You can make up your own idea. You can probably get it published. There are enormous numbers of such theories. But they all have some exoticism to them. They're difficult, and no one of which is so aesthetically compelling that we've just decided that that's the answer because the math told us so. And so we are trying to figure out what we can do more observationally. And the main path for doing this is to make more and more accurate measurements of the distances in the universe. Now, distances in the universe are hard because when you look at a galaxy up in the sky, you don't know if it's a really big galaxy far away or a really small galaxy right in front of your nose. And so really getting that perspective on things is very difficult. And so astronomers argued, including people here at Carnegie, argued about the size of the universe at the factor of 2 level for most of the 20th century. And yet we're now trying to do this to 1% and better. And so the goal of this lecture is to try to explain to you how we go about now trying to measure, or at least one of the methods by which we go about trying to measure the cosmic distance scale. So the main thing here, just to summarize, is this idea called baryon acoustic oscillations, a very fancy name. And this simply refers to sound waves propagating in the first 400,000 years after the Big Bang, so pretty early on. And this creates a very distinctive feature in the clustering of galaxies, and that feature is that pairs of galaxies are slightly more likely to be separated by 500 million light years rather than by 400 or 600 million light years. So a very small trend. But the reason this is useful is that if you can detect this pattern in the clustering of galaxies, then you can infer the distance to the galaxy. Just like if I tell you that I'm 6 feet tall, you in the back row can pull out a protractor and measure the angle from my feet to my head and figure out by comparing the angle to my known size how far away you are from me. And that's the idea that we're trying to do here. Okay, so that's the summary. Now I'm going to try to go into some of the ideas that underlie this. So we're actually going to start with something called the cosmic microwave background. This is the leftover radiative heat from the early universe. And when we observe it, it's millimeter wave radiation. We observe it all over the sky, and we get an exceptionally boring picture. That's the full sky. This is a very important picture because this says that the early universe is really a much simpler place. There are no major density fluctuations. Just everything is the same in all directions. It's actually one of the most important measurements in cosmology. But people didn't want to just stick around with this. They decided to try to make an exquisitely accurate measurement of the temperatures of this microwave background at all different angles in the sky. And they got this picture. This is turning up the contrast in that last picture by a factor of 100,000. So this is a 3-degree background above absolute zero. We're now looking in this picture at fluctuations at 100 microkelvin on top of that 3-degree black body. And this picture is very important because this is a picture of tiny density contrasts in the early universe, 400,000 years after the Big Bang. So these are very small fluctuations. And it's a very pretty picture. You can see fluctuations on large angular scales and fluctuations on small angular scales and fluctuations on medium angular scales. But if you let your eye drift over the picture, there's a characteristic angular scale about the size of one of these blobs like this. And that's the key thing. So if we take this map and we split it up into the amount of fluctuations on large angular scales, on small angular scales, on intermediate angular scales, we get a picture like this, where these are the large angular scales, these are the small angular scales, and there's this characteristic bump in the fluctuations at 1 degree. So that's the result of these sound waves in the early universe. So there's this peak in the fluctuations at 1 degree scale. And there's not just this peak, there's actually harmonics of the peak. So here's the second harmonic, the third harmonic. If those look a little impressionistic to you, here's the latest data, more recent data. So here's the first peak, first harmonic, second, third, fourth, fifth, sixth, seventh. You can probably squint and see the eighth. So these are harmonics in the early universe, just like the bass instrument we just heard. You have a string there. You can pluck the string and produce a fundamental mode, but you can also produce harmonics of that mode. And this is the same thing we're seeing here in the early universe. All right, what's happening with these sound waves? So the key epoch here is this epoch of recombination. Redshift of 1,000, when the universe is 1,000 times smaller, 1,000 times hotter, 1 billion times denser than it is today, about 400,000 years after the Big Bang. And this reason that this epoch is very important is that prior to this time, the universe is sufficiently hot and sufficiently dense that all of the hydrogen in the universe, which of course is almost all the universe, has been ionized. So instead of having electrons bound onto their protons, you actually have them separated into a plasma. And the reason this is important is that in a plasma, photons, light, cannot travel very far before it scatters off of a free electron and goes in some other direction. So in other words, if the air in this room all of a sudden became a plasma, in addition to all the other terrible things that we would be experiencing, we would not be able to see each other. So the universe, the air would become opaque. Okay, why does this matter? Well, because if you now take some of this plasma and you squeeze it, then the photons are trapped inside of this compressing region. As they get trapped, they're getting upscattered by the compressing walls of this infalling region. And this causes them to be shifted up to higher frequency, higher temperature. And this means that they have more pressure. Photons actually carry pressure. So as you try to squeeze this plasma, it actually is increasing its pressure, and that pressure will cause that region of space to expand again. The compression will get reversed, and will actually expand, overshoot, become too cold, at which point the rest of the universe pushes back, and that cycle just repeats. So this is really a sound wave, just like the sound waves in this room, except that the restoring force is not the random motion of the molecules in the air, but rather the radiation pressure of the photons. But aside from that, it really is a totally normal sound wave. And this is important because any perturbations you have, any density perturbations or pressure perturbations, actually just sit there and oscillate as sound waves. Just like if I had some balloon and popped it, it would just create sound waves. Okay, at recombination, the universe finally cools down enough that it becomes neutral. And that means that the electrons pair up with the nuclei and form neutral atoms. And that allows the photons to travel freely. Again, that's why we can see each other. The light can travel through the air because the air is neutral, not ionized. So at that point, if you have some overdense region, the photons leave, and the gas is left to try to collapse. And gravity will take it on towards a more and more overdense region. So perturbations will then grow by gravitational instability, and it's that growth of overdense regions becoming more and more overdense because of their gravity that eventually leads to the formation of galaxies and stars and so forth, eventually us. Okay, so that's the story of the sound waves. Now, why does this matter for our cosmological ideas? So let's imagine a toy universe where you have a universe that's only overdense at one location initially. And it's overdense in dark matter, it's overdense in gas, and it's overdense in photons. And because it's overdense in photons, it's also overpressured. And the way that an overpressure will try to equilibrate is by driving a spherical sound wave out into the rest of the universe. Again, just like if I have an overdense balloon and I pop it at the Big Bang pops the balloon, and the sound wave will race out towards you. So the sound wave travels outwards. It travels at the speed of sound, which is a pretty gaudy 57% of the speed of light. So it streaks outwards until it gets to this epoch of recombination. At that point, the photons decouple from the gas. The sound speed in the gas drops by like 5 orders of magnitude, and the sound wave just halts at some location. And so now you have the original region, which was overdense in dark matter, and this extra region, 500 million light years away, that is overdense in gas. And both of these regions, being overdense, will attract more material to them. You'll preferentially form galaxies at both locations, and this causes this very small tendency for galaxies to be separated by 500 million light years. Basically, the region that was good for forming one galaxy also created a sound wave which went out and helped form more galaxies at that extra distance of 500 million light years. Okay, well, so it's a very straightforward application of that physics, but the wonderful thing about it is that this distance of 500 million light years is something that's really easy to compute because it's just the distance that the sound wave could travel. So just speed times time. Very nice. And the microwave background anisotropies, the relative heights of all those peaks and troughs in that spectrum that I showed you, actually allows us to measure exactly the properties that we need to calculate this distance. And so today, we actually know this distance of 500 million light years to an accuracy of about 0.3%. So this is really wonderful. It's that, again, normally in cosmology, we do not know the intrinsic sizes of anything. We don't know how big a galaxy intrinsically is. We don't know how luminous a star is intrinsically. But this is a situation where the universe has given us something that we could really calculate, and we can calculate to 0.3%. So now we can use it as what's called a standard ruler. Basically, we can go out and measure it by angles and infer distances to things. Okay, well, life is harder than that, at least observationally, because it's not just that you have one point in the universe that was originally overdense. Every point in the universe had some variation in density. Every point in the universe threw off a sound wave. And so we're left trying to tease out this characteristic pattern of 500 million light years from an overall, very complicated map. And so to do this, we need to make very large maps of the universe. We're trying to tease out a very subtle signal, and it's on very large scales. I mean, 500 million light years sounds fantastically large compared to the Earth or the solar system, and it is, but it's also actually pretty large compared to the scales that astronomers often deal with as well. It's much larger than the scale of a galaxy or the scale of a cluster of galaxies. So we need to make very large maps of the universe. Okay, how do we do that? Well, one of the best ways to do it is with what's called a galaxy redshift survey. So what this means is that you go out and you make first images of the sky to make two-dimensional maps of where all the galaxies are. And then you turn that two-dimensional map into a three-dimensional map by measuring the Doppler shift to all those galaxies. And so with the largest maps, we now have about 1 million galaxies measured with their Doppler shift to make three-dimensional pictures like this, where this is the Earth here, and we're looking out across two large swaths here, and you can see all the large-scale structure of the big clusters and filaments and walls and the Great Wall and so forth. I asked my undergrads to calculate on this plot, when did the dinosaurs die? It's right there. Okay, so, all right, so I do this work with a survey called the Sloan Digital Sky Survey. It's the world's largest galaxy redshift survey. It's been using a dedicated 2.5-meter telescope in New Mexico above Alamogordo, if you've ever been to White Sands or Alamogordo. The project actually got started in 1990. It's been going a long time. Started taking data in 1998, and it's still running. And as Erica mentioned, we have new plans to operate until 2025 using now both the telescope in the north from New Mexico, but also now in the south with Las Campanas. SDSS is the world's largest compilation of extragalactic spectroscopy, and it's been really generously supported by the Sloan Foundation, Department of Energy, NSF, over 50 member institutions around the world. So it's a very large collaboration. That collaboration is really one of its biggest strengths. It's a really wonderful mix of scientists, and with SDSS 3 and 4, we've had over 1,000 people involved, and it's great because there's lots of different backgrounds and skills and interests, and the survey data is able to serve many different purposes, and so it really becomes this sort of federation of interests that come together to do one of these very large projects. It's not that the project is focused only on one particular deliverable. It's actually that it serves a wide range of deliverables, and that's what brings everybody together to do it. Okay, so SDSS, as I said, it operates on this 2.5-meter telescope. It's an unusual telescope because where's the dome? The dome is actually a shed that rolls off the telescope. If you were to walk over this cliff, beyond that railing, you would have a long drop. That's the side of the mountain. So it began by taking images of the sky, and it was really the first wide field digital imaging in the optical, produced lots and lots of beautiful images. Here's an example of the Whirlpool galaxy, nice globular cluster, pairs of galaxies, clusters of galaxies, all different sorts of objects. This is why the survey is so powerful. So this is then an image that comes from looking out. If you were to go out, actually about this time of year, and look up and had really good eyes, you would see this image above you if you could get rid of all the stars in the Milky Way. So this picture has taken away all the starlight and has just left the integrated light from all the galaxies. And you can see large-scale structure in here. You know, there are big lumps and some voids, but that's all very muted because it's all in projection. So to really see large-scale structure, you need to take this map and turn it into a three-dimensional map. Okay, well, we did this in the southern hemisphere too, so all told, it's been about 1/3 of the sky. It's 1 trillion multicolor pixels. If you want to know what 1 trillion pixels is, you go from here to here to here to here, and I can see the dots, but I'm not sure you can. So it's a very large amount of data, and this is all publicly available, has been for about 7 years. So if you go to Google Sky or Worldwide Telescope and you look in the northern galactic cap, you're probably looking at these images. Okay, well, we want to go to 3 dimensions, and to do this, we have to do spectroscopy. And what that means, we have to take the light from individual galaxies, which of course are extremely faint, and we need to take that light and break it up into a rainbow of colors and measure these characteristic atomic transitions in the spectrum. So this takes a lot more light than just making the image, because you need to take that light and break it up into 1,000 different colors and make these sensitive measurements. So we do this with something called multi-fiber spectroscopy. So basically you have a plate here, like this, and in that plate, holes have been drilled at the exact location of where the light from the galaxy will fall. And so you then plug these fibers into this and take the light down the fibers and off to the instruments. And this is the way that we can take spectra of 1,000 objects simultaneously. I would also like to mention that this is another idea that has a lot of heritage in Carnegie. Steve Scheckman did was the lead of one of the major multi-fiber spectrographs early on in the 1990s. Okay, so you have a plate, you plug the plate, you go out and observe the plate for about an hour, you throw the plate away, you take another plate, you go to a different part of the sky, you repeat and repeat and repeat. So we do this over and over again. Here is the team of people who plug the plates. These are all hand-plugged. We've done about 5 million fibers at this point. There was one month where we did 100,000. So it's hard work. When the plate's ready to be observed, it goes over here. It goes on the back of the telescope. This is actually the imaging camera, so this would come off, and the plate would go on. These are actually the spectrographs, and the light would go into the spectrographs. So again, the goal is to go from a sort of simple, flat image of the sky where you can see the galaxies in their angular location, but not yet in 3 dimensions, and to go to 3-dimensional maps by measuring the Doppler shift from the spectrum and using that to infer the relative distance to the objects. So this is an example, sort of toy example of doing that. So the next picture I'll show you is a small chunk of the survey, about 3% of the data of the survey, where I've taken a thin slice between 6 and 6.5 billion light years from us, and we've color-coded it where yellow will be the stuff on the front side, so it's only 6 billion light years across, and the stuff behind in purple will be 6.5 billion light years across. And this is about the size that you would see in a cell phone camera if you could point your cell phone up and take about that much of the sky. So this is about 3% of the survey data. From this side of the image to this side of the image is about 6 billion light years, and every dot in there is a galaxy. And you can see the large-scale structure now. If you look at the yellow dots exclusively, you'll see there's characteristic patterns there. And when you look at the red or the orange, which is slightly behind those galaxies, you see that the pattern is not the same. So you really can see the large-scale structure in this image. Okay, so now the job is to try to figure out, what does this tell us? Like, okay, so we've made a beautiful map, but now how do we actually go about inferring something about the properties of the universe, the composition of the universe? And for that, we'll do this with a correlation function. So the idea here is to pick a point in the survey, say the center one there, and we're now going to measure the number of galaxies around that in some annulus. And we'll do that as a function of radius. And then we'll repeat that count at all other points in the survey. And when you make that histogram, then you get a bump here. And this bump is you'll have to trust me on this, but this distance is 500 million light years in funny astronomer units. And this bump is actually exactly where this small signature from the early universe was predicted to be. This gave us a very clear connection. The physics we were seeing in the microwave background 400,000 years after the Big Bang was still present 10 billion years later, and we were actually seeing this in the galaxies. And moreover, it allowed us to measure the distance to these galaxies to 4%. And again, astronomers had spent the 20th century arguing about a factor of 2 here, so 4% was really cool. Today, the latest data looks something like this, where you have this peak here. Now this is measured to about 1% precision. And we can do it at a variety of redshifts. So here's 2% measurement to redshift 0.3, a 1% measurement to redshift of 0.57. The CMB itself measures this to better than 0.1%. So we're measuring the cosmic distance as a function of redshift, and this will allow us to infer things about the expansion history and in particular the acceleration of the universe. So what can we learn from this? Well, a very nice thing to look at is the idea of curvature of the universe. So Einstein says that the theory of general relativity says that the universe, that space-time can have a curvature, and in particular, the space of the universe can have a curvature. So of course, we're very familiar with the idea of Euclidean three-dimensional space. But it could be that we live on a surface of a sphere, a three-dimensional sphere embedded in four-dimensional space, but let's not worry about that. So you could basically imagine like we could live like an ant on a flat piece of paper, or we could live like an ant on a basketball, or we could live like an ant on some crinkled potato chip saddle-like thing. But these are valid things, and what this really means is that the curvature is really saying that the circumference of the circle is no longer 2 pi times the radius. Of course, Euclid says it's 2 pi times the radius. If you get out a piece of graph paper, that's the answer you'll get. But if you were to conform your graph paper to the surface of a basketball, you would actually not get 2 pi times the radius. If you set yourself at the North Pole, walked down to the equator, and then went all the way around, you would actually find that the circumference was 4 times the radius. So it turns out the acoustic peaks give a really wonderful measurement of this. We're able to measure the distance to things as well as the angles. It does really, really well at this measurement. But we also would like to understand dark energy. So in particular, we would like to understand, is the cosmological constant really constant? We measure this dark energy density. Dark energy, is the energy density constant in time as the cosmological constant would predict? But maybe it's something else that would vary over time. And cosmologists tend to parameterize this as W. So W of minus 1 is the cosmological constant. Everything else means that dark energy is changing in time. So let's see some of these measurements. So this is distance versus redshift, some points from SDSS, some points from other surveys. So that's just measuring the cosmic distance scale. And the next line I'll show you is the prediction for this curve from the microwave background data, assuming that the universe is flat and that the dark energy is a cosmological constant. And that gives you this curve. There's no extra parameters in here. That's where the prediction goes. So this says that the data is actually really consistent with a flat universe and a cosmological constant. If you zoom in, divide out by the smooth curve, you get these percent level agreements between the data and this model. And if you were to pick other models, such as models that have a small curvature, this would be a 1% crinkling, or that dark energy is changing over time. Here's a case where dark energy is halved since redshift of 1. And you can see they're not as nearly as good measurements or fits to the data. So the data really does prefer this flat universe with a cosmological constant. Here's another plot of this where you have a flat universe and a cosmological constant universe, and the data is driving us back to this little region around this. So this is a really interesting thing. We have this, we've given the data a chance to open up, in some sense, the simplest model, and we've given the data a chance to open up 2 different new directions, and the data's driven us back to the simplest model. So this is really a strong encouragement for this interpretation. Okay, so in cosmology, we've kind of, we're in this interesting situation where we have this very concrete and simple and elegant theory for how the universe works that's been tested from an age of about 1 second after the Big Bang until today over a very wide range of length scales and mass scales and time scales. And it does really well. And it gives us, it's not only that it's been validated, it also gives a very predictive theory for how structure will form and how galaxies will form. So it's wonderful. But to make that theory work, we have inferred 2 new things: an unknown type of matter, dark matter, and some new force in the universe that's accelerating the universe. And we don't know what these things are. So cosmology is in this really wonderful state that we have an incredibly predictive and well-tested basic framework, but it involves 2 new components that we haven't yet discovered in the laboratory. So, of course, people are very excited to go on and measure this more and more. We're just at a point where new facilities are going to improve these maps by a very large amount, factors of order 100. I'll mention DESI a bit more here, but this is at the Kitt Peak 4 meter. There's a new project called LSST, big satellite called Euclid, the Giant Magellan Telescope that's we're building here. So, I mean, there's just a wide range of cosmological measurements that we're going to be able to complete in the coming decade. I'll just mention DESI. So this is intending to take, instead of measuring 1 or 2 or 3 million galaxies, we're going to be trying to measure 35 million galaxies and quasars out to a redshift of 3.5. This will be on the existing Kitt Peak 4 meter telescope. It's an old telescope, but this is going to be replacing all this stuff at the top end of the telescope with a much bigger instrument. And so here's a picture of the corrector optics that's being completed now. And instead of having just 1,000 fibers that are plugged into plates, this will use a robotic set of fibers with 5,000 fibers, all of which are individually positioned by these little robots that move around in about of order 30 seconds to put the fiber where it needs to be to about 5-micron precision. So we're hoping to have first light on this instrument next year and then be starting the survey in 2020. So to conclude, I've tried to explain to you that acoustic oscillations, sound waves, provide a very robust way to measure the cosmological distance scale and to infer the properties of dark energy. And it has a lot of really nice properties. It's a very simple physical picture. It's really quite familiar in terms of how sound works on Earth. And it leaves a very clean signature in galaxy clustering. And it's now become a very important tool in the study of the cosmic expansion history and dark energy. And within SDSS, we've used the acoustic peak to measure the cosmic distance scale to percent level accuracy. We found excellent consistency with the universe, with a simple cosmology of flat curvature and a cosmological constant. But this is really just whetting our appetite for trying to figure out more and more about what dark matter and dark energy are. This will leave a lot of opportunity for the next generation of astronomers. And we can only say, challenge accepted. I hope you'll go and try to learn more about the survey at sdss.org, and I'll be happy to take any questions you have. Thank you.
I have a feeling there are some questions. Right
Please.
there. All right. And will you please repeat the question?
I understand this is a bit abstract, and they might have missed something, or I might just be missing something. Never mind that I just repeated my statement. You were mentioning earlier about the standard ruler measurement, where given the angle and the distance of the object, you could figure out the size of the object. You could calculate the distance to the object.
Right.
First of all, do we know over a large scale the general curvature of space-time, for example, saddle, spherical, Euclidean? And since that the geometrical standard ruler calculation takes place on Euclidean geometry, would space-time overall being a different geometry affect that calculation, or just local curvatures as well?
Yeah, so the question is about how the spatial curvature affects this interpretation of standard rulers. If, in other words, if I tell you how tall I am, and you measure an angle, and you want to infer the distance, you're doing that in a Euclidean flat geometry. In fact, the calculations are done in the full curvature. So if you include a spatial curvature, then you will infer a different distance to it, and that's all self-consistently included in the calculations. But really, that's why this is a very useful thing, because effectively, by the standard ruler, when you measure at an angle, you're measuring something about circumference. Like really what you're doing is you're saying that this much angle is corresponding to this much distance. That's really saying something about circumference. So now, when you can get anything about the radius, then you've really measured exactly this curvature effect. And so that radius comes from basically understanding things about the expansion history of the universe. But that's really why the curvature comes out so well. You would not get it if you only measured at one redshift. You would not be able to disentangle these effects. But when you measure at multiple redshifts, the curvature comes in differently. Please. Yes. So the question is, are the photons, prior to 400,000 years, when the universe is ionized and the photons are scattering, are they still moving at the speed of light? And the answer is yes. They are moving at the speed of light. That said, it doesn't mean that they're going to travel from point A to point B at the speed of light if they get scattered multiple times as they try to get there. So when you scatter a whole lot, then you actually have to sort of eventually random walk your way out to larger distances. So their ability to travel, their instantaneous speed is the speed of light, but their ability to get anywhere is really retarded by the multiple scatterings. Yes?
What is the speculation of what is happening in the first minute?
In the
First minute.
Yeah, so the question is about the first minute. So you used the word speculation correctly, thank you. So, I mean, I think that we know substantial things about the universe from 1 second on, and that's because the formation, the fusion of hydrogen into helium and deuterium and lithium really happens in the first few minutes of the universe. And so if the universe were very different then we would get a different abundance of those elements, and the abundances that we measure of those elements matches really well to inferences that we make in the microwave background much later. So I think that gives us some confidence that things are okay back to 1 second. Earlier than that is really hard to, I mean, it's just really speculative. The only probe that we really have that goes earlier than that, well, we have, okay, I would say that we have some examples of things that didn't happen. Because it's definitely possible to dream up extensions to particle physics that cause things to happen then that don't go away, that leave some long-lived relic or otherwise cause something really dramatic to happen later on. So in that sense, we do know things about things that didn't happen. I'm sure you'd be more interested in the things that did happen, and so that's where things get hard. Of course, there's these concepts of cosmological inflation in the very earliest moments, and I think we have corroborating evidence that support that idea, but that's different from proof, and so we're in that situation. Yes.
Could you please re-explain why the speed of sound was comparable to the speed of light in the air?
Oh, happy to, yeah. So the question is about why is the speed of sound at these early times 57% of the speed of light? And indeed, that's not so clear. So the thing to remember about sound is that it's a competition between pressure forces and the inertia of the fluid. This is true even in this room. Like, what sets the speed of sound in this room? It's the ratio of pressure to the inertia of the gas. And what's happening in the early universe is that radiation pressure is really, really large compared to the mass in the gas. That can seem hard to believe because the temperature back then is only 2,700 degrees Kelvin, which is not that much higher than a steel furnace, right? And yet nobody talks about relativistic sound waves coming out of steel furnaces, right? And the reason is that the density on terrestrial scales is enormously larger than the densities in the early universe. So the radiation forces are just completely pushing the protons and electrons around at their will, and that causes the speed of sound to be enormous. Behind you, yes.
So taking this analogy with normal sound, that depends on density. How well do we know the density, and what's the uncertainty there in the speed of sound then?
So we know the density actually quite well, to about 1%. So the question is, how do we know the density? So because the speed of sound does depend upon the density. I just said that the speed of sound is the ratio of the pressure to the density. The pressure is coming from the photons, which we think we know, but the density that we're concerned about here is a mixture, actually, of the density of the energy density of the photons and the density of the protons. So you're right to ask, how well do we know that density? So it turns out we know that to about 1%. And that comes from the relative heights of the peaks and troughs in the microwave background spectrum. If you have the more, I showed you those harmonics earlier with count up to 8 harmonics. It turns out that as you increase the baryon, as you increase the gas density in the universe, it makes all the odd peaks higher than the even peaks. So you get this odd even asymmetry in the peaks, and that gives a very, very strong measurement of the density. Please.
Was that transition 400,000 years ago just a matter of dropping below the point at which plasma stays plasma?
Yes.
Excuse me. And reverts to sort of a more normal material universe?
Yeah, so the question is the transition 400,000 years after the Big Bang from ionized to neutral just because the temperature is dropping? And yes, it's really just that. I mean, you have, how to say this? So electrons and protons want to combine, like the energetic lead is favorable for them to combine, but if they combine and there's some other photon that can come along and cause them to split apart again, then it's a question of which process is faster. And as the temperature drops, then the number of photons that are around that are energetic enough to ionize that atom drop too much in their abundance. And so the combination reactions win and the universe transitions. It doesn't happen instantaneously. It takes about 40,000 years. But you do your best. Over here.
Has the speed of light always been the same, or is it a constant, or could it have been faster or slower in the early universe?
So the question is the speed of light always constant, or did it change? So my answer to you is that the speed of light is constant, but you should remember that it.
I know it is a constant now, but
Yeah, but even in the past, so I would say it's a constant. But one needs to remember that in general relativity, the distances of space are changing. So you can decide what you make of that. So when we talk about something at redshift of 1,000, if the light travels a year, then it has gone 1 light year. That's a fixed distance, about 10 to the 18 centimeters. But that's the distance that you would measure if you were back then. Today, that distance has expanded to 1,000 times that distance. So we interpret that as the speed of light being constant and the distance is changing. If you chose to take the reverse view, I think there are ways to make the math work out that way if you want. So, in the way back, but you're going to be very loud. I'm not hearing super well.
Is the apparent age of the universe the same when viewed in all directions?
Okay, the question is the apparent age of the universe the same viewed in all directions? So the answer is yes, as far as we know. So really, that statement is a statement of isotropy of the universe. Do we see the same cosmological parameters looking in different directions? And we do. So for example, in the, I won't be able to go back that far, but in that picture of the microwave background sky that I showed you earlier, like the very first picture with the incredible detail of that picture, we can then measure the statistics of the map in this direction, and this direction, and this direction, and get very consistent answers. And so that's an example of just the fact that the universe really does appear to be the same in different directions. This is something that we try to test. It's not really something that people expect to see differences in, but it's something that people do try to test to see if indeed that isotropy bears out. Over here.
Could the universe be curved, this space be curved, but we're just not able to measure the curvature yet?
Absolutely. So the question is, can the space be curved, but just at a level that's sufficiently hard to measure? So absolutely. So let's take a beach ball as an example. So the ball has some size, but if you're only looking at some little patch, then you don't really notice it yet. And so really our limits on curvature, when we say the universe is flat, what we're really saying is that the radius of any curvature, meaning the radius of the ball, is really large compared to the scale that we've been able to measure. And in detail, the constraints are that the radius has to be about 10 times larger than the visible size of the universe. You can decide, but that's not infinite, right? So it could be that the universe is curved on some scale that we just haven't been able to detect yet.
Was it affected by the size of the observable universe?
Sorry, was it?
Is it affected by the size of the observable universe?
Is the question is this curvature affected by the size of the visible universe? Oh, the accuracy that we measure. Oh, sure, yeah, absolutely. So the accuracy that we can measure anything is determined by how many examples you get to measure. If we were astronomers 10 billion years in the future, we would have more sensitive measurements. We could just wait.
Let's take 2 more questions. I saw someone back there.
Yes. Again, pretty loud, please.
Could you please share with us your favorite nerdy math joke?
Oh, dear. Can I share my favorite nerdy math joke? I'm afraid I don't. I'm not very good at remembering jokes. I'm sorry, I don't think I can comply. In the far back.
Good explanation for the triggering from cosmic inflation, current understanding of it?
Sorry, could you...
What's the current understanding of the triggering of cosmic inflation?
Okay, so the question is about cosmic inflation, which was not... so let me just describe a bit about inflation. So inflation is this idea that in the early universe, the universe enters into some period where it undergoes exponential expansion. And the end of that expansion, at the end of that expansion, all the energy density that's been created by that gets converted back into normal particles, and our universe proceeds from that. Which, of course, begs the question is what was happening before the period of exponential expansion? And the answer is we honestly don't know. There's lots of theories. Some people will say that, there's just some quantum foam of stuff that's sort of popping off exponentially expanding regions in various places, all of which have their own different fate. But it's very speculative. And indeed, I'll leave you with just the idea that we all think of the Big Bang as this instantaneous moment where everything starts. But I think increasingly we're in the situation in modern cosmology where that's not actually a very good description, it's not a very good application of the idea of the Big Bang. Because when we think about the Big Bang, what we're really saying is that there's an expanding universe that's smooth and hot, and that really is the description of the end of inflation. So in many ways, I think it's more accurate to think of the Big Bang as the end of inflation, and leaving the question of what might go on before that. Okay, thank you.
Set your alarms for tomorrow at 10. And Dr. Eisenstein will be here for a few more minutes if you want to ask more questions to him.